There's a boundary around a black hole where the escape velocity reaches the speed of light. Cross it and nothing gets back out. Not matter, not light, not information. It's called the event horizon, and for a century it has been the most confidently described thing in physics that nobody had ever actually observed. We knew where it should be. We knew what it should do. We had no direct evidence it was there. In June, researchers reported detecting its fingerprint for the first time. Not a picture of it. Something stranger and, in a way, better. The sound of one forming. Start with what an event horizon isn't, because almost everyone pictures it wrong. It isn't a surface. There's nothing there. No shell, no membrane, no wall you'd hit. If you fell through one on a large enough black hole, you might not notice anything at all at the moment of crossing. It's a boundary defined entirely by consequence, the place beyond which every possible path leads inward. You could no more bounce off it than you could bounce off next Tuesday, which is precisely why proving it exists is so awkward. Anything that would confirm it directly is on the wrong side of it, permanently. You cannot observe the thing whose defining property is that observations don't come back. So the trick is to listen for what a horizon does to something else. When two black holes spiral together and merge, the object left behind is violently misshapen for a moment, and it settles down by radiating gravitational waves, ripples in the geometry of space itself. Physicists call this the ringdown, and the name is apt because it behaves like a struck bell. The tones it rings at are set by the mass and spin of what's left. Here's the part that makes it a test. If the merged object has a true horizon, the ringing simply fades because energy traveling inward is gone for good. If instead it had some kind of surface, and there are speculative alternatives to black holes that propose exactly that, some of that energy would reflect back out, producing faint repeats. Echoes. Nobody has ever convincingly found echoes, and the new work goes further, matching the fine structure of the ringing to what a genuine horizon predicts. It's evidenced by absence and by shape. The bell rings the way it should, and then it stops properly. Now, how do you hear a ripple in space? The detectors are extraordinary and worth understanding. A gravitational wave passing through stretches space in one direction while squeezing it in the other, so you build an L, kilometers along each arm, and bounce laser light up and down both, watching for one arm becoming very slightly longer than the other. Very slightly is doing a lot of work. The change being measured is a small fraction of the width of a proton. These instruments can detect a passing distortion smaller than an atomic nucleus across a 4-kilometer arm, which is why the first detection in 2015 was treated as one of the great experimental achievements of the century. It's worth asking how confident anyone was before this, because the answer is very on excellent but entirely indirect evidence. Astronomers spent decades watching stars near the center of our galaxy whip around something invisible on orbits so tight and so fast that the mass inside had to be millions of times the sun's, packed into a region smaller than our solar system. Nothing known can do that except a black hole. Separately, matter falling toward these objects heats to the point of glowing in X-rays, and in 2019, a global network of radio telescopes produced an image of the shadow one casts against the light behind it. Every piece of that pointed the same way. None of it touched the horizon itself. And the horizon is where the deepest problem in physics lives. If information that falls in is genuinely destroyed, that contradicts quantum mechanics, which says information is never lost. If it isn't destroyed, it has to get out somehow, which contradicts what the horizon is. Physicists have argued about this for 50 years, and the whole argument rests on the horizon behaving exactly as described. Testing that boundary isn't a tidying up exercise. It's checking the foundations under the disagreement, and this is the shift nobody outside the field has fully registered. In 2015, there was one detection, and it was historic. The latest catalogue adds 161 new collisions in a single release, bringing the running total to around 390. Something that was a once-in-a-lifetime event a decade ago now happens most weeks the detectors are switched on. That change in volume matters more than any single event because it turns astronomy into statistics. With one black hole merger, you have an anecdote. With hundreds, you have a population. You can ask how heavy these objects typically are, how fast they spin, how often they pair up, and whether the distribution matches what theories of stellar death predict. It already doesn't, quite. Some of the objects being found are heavier than the standard picture of collapsing stars comfortably allows, which suggests some of them are built from earlier mergers. Black holes made of black holes assembled over cosmic time. One recently reported pair looks like a record breaker on mass, and each of those outliers is a constraint on where they can possibly have come from. Meanwhile, the other end of the black hole business is producing its own surprise. The supermassive ones at the centers of galaxies drive enormous outflows of gas, and new measurements suggest those winds carry something like 100 times more power than previously estimated. That sounds like a niche correction. It isn't. Those winds are the mechanism by which a black hole talks to its galaxy, pushing gas out, heating it, shutting down the star formation that would otherwise continue. If the winds are far stronger than assumed, then the influence of a single object, tiny compared with the galaxy around it, is much larger than the models allowed. Galaxies and their central black holes grow in a relationship, and we've apparently been underestimating one side of the conversation by 2 orders of magnitude. There's one more capability worth knowing about, because it changed what gravitational waves are for. In 2017, the detectors picked up 2 neutron stars colliding, and within seconds, telescopes around the world swung to look at the same patch of sky and saw the explosion in ordinary light. That was the first time an event was observed through both gravity and light at once, and it settled several arguments immediately, including where a good deal of the universe's gold and platinum is manufactured. Gravitational waves stopped being a way to confirm Einstein and became a way to be told where to point everything else. It's worth stepping back to see how fast all this has moved. Black holes were, for decades, a mathematical curiosity that many serious physicists expected to be an artifact of the equations. Einstein himself doubted they were physically real. Within a single human lifetime, they went from probably not to observed indirectly, then imaged as a shadow, then heard colliding, and now confirmed to have the one feature that makes them what they are. There's a nice irony in how the confirmation arrived too. The horizon is defined by the fact that nothing escapes it, so the only way to study it was to find a phenomenon that doesn't need to escape. Gravitational waves aren't emitted from inside, they're generated by the warping of space outside. We didn't get information out of a black hole. We read the shape of the dent it makes on the way to becoming one. What's coming next changes the pitch. Ground-based detectors are limited by the length of their arms and by the Earth being an inconveniently noisy place. Traffic, weather, seismic rumble. A detector in space, with arms measured in millions of kilometers, would hear far lower frequencies, which means far larger objects, the supermassive black holes at galactic centers merging when galaxies collide. Those events are currently invisible to us entirely. That's the mission being built toward. So the honest summary is that a century-old prediction has finally been tested against the one property that defines it, and it held. There is a real boundary out there, around real objects, that genuinely deletes whatever crosses it, and we know because the ringing stopped exactly the way it was supposed to, which leaves a question worth carrying, and it's about method more than physics. If the way to confirm something invisible was to listen for the echo that never came, what else are we currently failing to detect simply because we're looking for a signal instead of a silence?